Hey folks, my name's Ed, and today I want to tell you a story about carbohydrates. In our story, we'll have two characters, the first of which, in blue, is a monosaccharide, and it is beta-D-glucose. In red, a disaccharide, we have alpha-alpha-D trehalose. Now, the setting of our story is within a bacteria cell. Within this cell, these two sugars are glycosylated. They are connected to one another to create a trisaccharide. Isobemiose is a carbohydrate that this fictitious bacterium uses to strengthen its cell wall. Now, if it has a very formidable cell wall, it is able to protect itself from its environment adequately. As avid organic chemists, we want to try and synthesize this trisaccharide. However, we do not have the enzyme that is used to catalyze this reaction. Using a variety of reagents and solvents, we're going to be able to synthesize this trisaccharide. Now, unfortunately, we're going to have two different types of linkages formed, therefore we'll have two different compounds. Now, to overcome this problem, we need to master the unique chemical properties that surround carbohydrates. But before we can jump headfirst into this issue, we're going to have to get a couple basic principles underneath our belt. The first of which is carbohydrate terminology. After we familiarize ourselves with the terminology, we're going to be able to move on to structures. Once we have these two principles mastered, then we're going to explore the chemical characteristics of sugars. Our running example for this video will be glucose. Now, I took the liberty of drawing Fischer projections of our glucose molecule, and I felt it was important to point out that there are two types of glucose molecules. Now, there's D-glucose, which is on the left, and there is L-glucose, which is on the right, and you guessed it, they are enantiomers, which means they're mirror images of one another. Now, in nature, we will find predominantly D carbohydrates. Okay, so I took the liberty of drawing on the left a structural isomer of glucose. It is another D sugar, and it is D-fructose. Now, the key difference between these structural isomers is the fact that glucose has an aldehyde group as its carbonyl, and fructose has a ketone as its carbonyl group. Now, the presence of an aldehyde in the sugar makes it an aldose, and the presence of a ketone in fructose makes it a ketose. Now, to the far right, I drew a similar aldose to glucose. The one difference is at the C4 carbon. I numbered the carbons, and if you look at C4, let's get a different color, you will notice that the OH group is flipped compared to the far right Fischer projection. Everything else is the same, except for at this position. This is a diastereomer, but it has a very special name for our purposes. Due to the existence of several chiral centers and the fact that one chiral center differs, this diastereomer is called an epimer. Now, the epimer that I drew, it is a C4 epimer, and it is D-galactose. I just remembered I forgot an important distinction between ketoses and aldoses, so I'm going to quickly wipe the board. Okay. These ketoses and aldoses normally do not stay in this straight carbon chain, in this acyclic form. It's not thermodynamically favorable. So in solution, in water, when the sugar is dissolved in water, you're going to see it in a ring structure. A ring structure, I'm sure you're very familiar with when you look at biology textbooks and organic chemistry textbooks. These ring structures I drew down below are called Hawthorne projections. Now, they make it look like the ring's flat. We know it's not, so we add a little bit of red, and that is supposed to signify that this end of the ring structure is lifted up or towards us. Now, the ring structure is predominant. The straight chain carbon structure, it is a very, very small percentage of it is present in solution. It's still there, but it's a very small percentage. So don't freak out when you look at these rings. I know that I did not put the hydrogens. I just did that because for space sake, I don't want it to be cluttered and to be confusing. So the hydrogens are there. They are there, I promise. I just didn't draw them. Like I said earlier, when an aldose cyclizes, it does so because it is thermodynamically favorable or energetically favorable for it to do so. It cyclizes and forms a hemiacetal. By contrast, a ketose, when it cyclizes, it forms a hemiketal. Another name for the D-glucose molecule I drew below is a pyranose. So you can call it D-glucopyranose. The name pyranose comes from a molecule called pyrin, or pyran, however you want to say it. Now the name of the fructose ring, fructose sugar, is furanose. So we have fructofuranose. And you can probably guess it is named after a very similar looking molecule called furan. Now quickly, the last thing I want to do in this video is show you how this cyclization process happens for glucose. What's the mechanism behind this thermodynamically favorable mechanism? Right, so here's our glucose molecule, and I'm going to lay it on its side. I'm going to lay it this way so we can better understand how this mechanism occurs. We also want to rotate the molecule, because it's a carbon-carbon bond, it can rotate around the C4-C5 bond. Now, rotating that makes us have a very pseudo-Hawthorne type projection, which will make it easy for us to see how this mechanism occurs. Like I said earlier, hydrogens are there, we just omitted them because they're pesky and bothersome. Now, because we are in solution, this extremely nucleophilic aldehyde's probably going to protonate. It's going to snag a hydrogen from a water molecule that passes by. It's also worth mentioning that I took the liberty of numbering our carbons, so carbon 1 is the aldehyde group. So now that we have the protonated aldehyde, we will have a resonance form to do. And with that positive charge on the oxygen, we're going to see it be attacked by a nucleophilic hydroxyl group on C5. That will cause electrons to bump onto the hydroxyl group. And now let's draw the newly created six-membered ring structure. It's worth mentioning that when that nucleophilic hydroxyl group attacks, it can attack from the top or bottom face of the ring. So that's going to give us two products. Let me quickly mention that I did drop a proton right up here. Water would just come by and snag that bad boy off of the endocyclic oxygen, or the oxygen within the ring. Now, these are both still D-glucose molecules. They are still D-glucopyranoses, but at the C1 position where the aldehyde was, we created a new chiral center. Now, depending on where the nucleophilic hydroxyl group nuked into the aldehyde, that determines what type of anomer we have. So these are called anomers. Now, the new chiral center that's made at the C1 position, that's called the anomeric carbon. I'm going to put a star next to it. Now, if the hydroxyl groups are trans, or one's up, compared to the C6OH group, then it is the alpha anomer, so alpha D-glucose. By contrast, if they're cis, or the same side as the C6OH group, then it is the beta anomer. This will become important when we move on to glycosylations in the next video. Unfortunately, we ran out of time. This is Ed, and I will see you next time.